I'd like to now introduce Alexandre Costa, who holds a master's and PhD in civil and earthquake engineering and has additional training in disaster risk reduction for cultural heritage. As co-founder and partner of his company, he's also invited professor at the Faculty of Architecture of the University of Porto and the Polytechnic Institute of Porto. So, on that, thank you.
Thank you very much, Tom. So good morning to everyone. It's a pleasure to here to presenting this work. And what I'm going to present here, let's say that is it was really a challenge how to do it and why we do it. It was a replacement of a column at the Convent of Christ in Portugal. So this was part of the team, also two other members from my company in CREP, and also it was also involved a part of the constructor in the end to implement it on site. So just a brief introduction regarding the Convent of Christ. It is a World Heritage Site since 1983, and it is located in Tomar. And the purpose of this doesn't work there. And the purpose of our intervention was in that part, in that part between those two cloisters. And why was it required this kind of intervention? Just to understand a bit better the monument, like it was started to be built on the 12th century to the 17th, and it was involving a lot of different architectural part and history of Portugal. And it is very famous, for example, for the Charola, the Romanesque Charola, the cloister of the King John III, and also the famous manually window that every architect in Portugal usually they studied in the history of architecture in Portugal. So let's just go more briefly. So these these parts that I was showing you, the famous Manuelino window, the Charola, where the knights were there for praying, and then here the staircase made on stone. So what was the objective? It was to ensure the structural stability of part of the structure. It was one specific room because there was a central pillar, central column that was supporting upper floors, and it was in an advanced state of material degradation. This just to also exemplify the collaboration between the different entities. The first one on the left, it is like the responsible for management and also to test the interventions on this kind of monuments in Portugal. Then we are the designers of intervention, and here you have the constructor that was responsible to implement it on site. So we were working closely together. So just where was the problem? You see on the left figure at level 0, it was a limestone column that was supporting a vaulted floor from level 0, also supporting a vaulted floor and walls from level 1, and then supporting walls on the second level as well as the roof. And here on the right, you can see already some problems that were related to the material itself, because the column was supported directly on the soil. And this is a problem that is also documented in many other parts of the convent. And in this particular room, it was very important because as it was supporting many other parts of the structure, you can see now here the column. You see it's more better in the top, but then as it is going down near the soil, it has a lot of material degradation. These are photos from level 0. You can see also the vaults. Then level 1, it was there, not precisely aligned with that column. There was a small offset. And then on level 2, we still have also this masonry wall. So all this load was going to that column. So we did inspection diagnosis, just to evaluate what was the problem. It is also happening at the other parts of the convent, and is related mainly to the, let's say, to the material itself. So the upper part was not presenting any significant damage or cracks or any other stuff that could be related also to some settlements, but it was related and the damage was concentrated at level 0. So I should run, otherwise Tom is going to stop me. So the damage was concentrated at level 0, and now you can see here some close looks. You can see like vertical cracks were already on the column. Some of them was going from one side to the other and also along the height of the column, many other parts. It was originally a cross-section of 50 centimeters, and at the base you have the reduction up to 15 centimeters, so this means that we are getting almost lower than half of the cross-section that we needed. That was originally there, and these vertical cracks were inducing, or were indicating that we had a permanent compressive strength, stresses that were close to the strength of the column. So the cause was related to the porosity of the material, also the humidity that was around. So, unfortunately, the final decision came out and was to replace this column. So let's go up. So the point that I'm going to show you here and spend more time is how we could design or how could we do this replacement of this column, minimizing the intervention on the rest of the structure. So we designed and implemented a temporary scaffolding system that was adapted to local conditions. So we could go inside the column, take out temporarily the load from the column, replace it, remove it from the room, put a new column there, and then put it back to not original condition, but the strengthening conditions. So this is what came out from the solution. Of course, that I would say the concept now may look not simple, but well, the idea can be simple. It was hard to achieve it, but just to explain briefly the idea. So we had there the vertical load coming to the column, and the idea was to sustain the load. I would like to point it out, but sustain the load at the upper part, and how we could do it with these struts that were placed there, connected to some of these foundations, temporary foundations that were built on site, like separated from the original structure, and we could do it because we have archaeological excavations and there was no archaeological artifacts over there. So this was a temporary structure, and then the idea was to, as we have the vertical load, if we pre-stress these tie rods, we are going to tighten the base, and tightening the base, we are going to put an upper force that will counteract the gravity loads that we had on the column. So that was the main concept that we developed, and now I'm going to show you, so the purpose on site. So you see there a lot of information, visual information, but I will try to detail what is that. So on the bottom you have the temporary reinforcing concrete foundations with the divided rebars connecting the four foundations here that were connected to a hydraulic system. Then you have like those vertical small elements that were placed there for the monitoring system during the activities. Then you have the big steel braces that were there to connect it to the top. So now you have here some more details. Let me also rephrase one thing here. That is, if you take a look here on the right, can I take this out? If you take a look here on the right, we are connecting the force upper the capital of the column. The purpose was to control the stresses that we're inducing in that element that was connecting all the arches and leave out the capital alone. And you can see this steel profile that is there just for the supporting of the capital, because there could be a connection between the capital and the column, and we wanted to separate and on one hand avoid the downward movement of this capital, and in the other hand allow to remove this column. So the next slide is just like a detailed drawing from the system. So in order to ensure a proper connection between these upper parts and the stone, and you can see there on the left, there was placed some neoprene small plates, neoprene layer, and then it was casting in place. I like really to point here, but well, there was a small caps built in place in reinforcing concrete, separated from the stone with a neoprene, so we could control the stresses that we induce in that element. In this way, we could have good connection between our strut and the structure, but separating and not inducing any more damage. Then we pre-stress with these DV ducts at the top, and then we started to lift it. In order to control it, we control this with a monitoring system. Just also to show other entities that were involved. That first one, STAP, was responsible for the hydraulic system to control the forces that we gave to the constructor to control it during the works. Then OZ is another company that was doing the monitoring of the vertical movements of the arches, and more precisely and more important, the relative movement between the capital and the column, so we could be sure that we are not lifting, but at least taking out the vertical load from the column. And this was made with conservators, archaeologists, etc. So what we are going to see now there on the left, it was once there was the uplift of the load. So you can see there it was like 3 millimeters. We just want a smaller flip to see first if there was any gap between the capital and the column, so if it was necessary to remove something or not. So we were lucky because it was able to do it. And here in the middle, you are going to see after, you can see now that the area is more or less now clear. Just see the struts. Then you can see there a small railway. And if this works, or if you can help me pressing the figure in the middle, no, back, sorry. If you press there in the middle, let's see if it works. There's a video there. Yes, perfect. So you can see that you have that small train that was removing the column, and we were keeping all the other stuff in the top. So this was not the most stressful movement. The most stressful movement was when we were applying the loads. We could really see the footings moving on the ground. And then, of course, it was removed, it was replaced. You can see the reduction of the cross section. And then in the end, it was placed another one. So the main challenge was also not to implement this, but then how could we remove it and how we could put another one. So now I can pass to the next slide. Okay. Yeah, and here you can see on the left, the new column coming from the door, a small railway again, and coming to the new place. So it was necessary to remove the column to identify the correct dimensions and then put it back again. And then in the end, just remove the footings, temporary footings. They were removed, they were demolished. The main idea first was then to reuse it, but then they were demolished, and in the end it was just put again the soil and finish the intervention. So thank you very much for your time. Thank you, Tom.